Space, the final frontier.
Welcome back to our New Year's lecture from Behavioral Health 2000. Today our theme is predictions and why it is so difficult for us to accept predictions and to incorporate them into our thinking, our belief system, and our actions. Now we begin by going back a century, namely to Albert Einstein. And here he is in the first image. You see him sitting there with a whole bunch of physicists at the Solvay conference, an occasion where the Illuminati of physics in Europe after the First World War were getting together debating the new science of quantum theory. So here is Albert. He already had completed the theory for which he has become most famous. But before we go there, we need to set the stage. What did Einstein face when he was trying to understand gravity? And in the next image you see Newton, Isaac Newton, and his famous formula of the force of two bodies attracting each other through gravity. So the force F is then the gravitational constant, Newton's constant, and the product of the two masses, m1, m2, let's say the Earth and the Moon, divided by the square of the distance. This is the famous inverse square law of gravitation. This law was extremely successful. It generalized. It didn't only apply to things on Earth, but it applies to the entire solar system and as far out into the universe as you might want to go. Now there is a problem, and Newton himself realized that this formula has a deficiency. You can see there is no term for time. It is as though the force acts instantaneous. There is no traveling of the force. There's nothing describing what mediates the force. And Newton said as much. He said, I give you this formula and I have decided it works well. However, what exactly the force is, I will leave to those after me to analyze, discover, and describe. Okay, so Einstein then was faced with these deficiencies in Newton's concept of gravitation. And he analyzed gravitation in a completely different way. We don't have the time here and the space to go into the 10-year process that he struggled with this labor of love and sometimes desperation. Einstein was great in math. It's an illusion that he was not good at math. He was terrific at math, but he had not studied some aspects of math like analytical and differential geometry that were required for him to deal with the changes in space-time produced by gravitating masses in the universe. He had help from his friends in Zurich, math professors. Marcel Grossmann is a famous name, who pointed him in the right direction. Now eventually he was successful, and he came up with this very condensed formula that the left-hand side here describes the gravitational mass that's present here in this particular instant, and on the right-hand side there is a so-called tensor, the curvature of space-time. And you can see there is the c to the fourth power is the speed of light. So there is an implied time dimension in this formula. And at the lower part of the slide, you see this famous statement, space-time tells matter how to move, and matter tells space-time how to curve. So in Einstein's conception, there is no force that acts on a gravitating body, but rather there is a dance whereby bodies or masses interact with space-time by shaping and deforming it. And any spaceship flying by then just follows the curvature of space-time rather than being impacted by a immediately force at a distance action. It's rather a rearrangement and a reorganization and architecture of space-time that appears to us as though it's a force pulling us towards a heavy body. So that was the radical reconception that Einstein developed. Now, using his equations, Einstein could make a prediction. Namely, if light comes through us, to us, from a distant star, passing close by the body of the sun, then the gravitational distortion of space close to the sun should deflect and reorient the light coming from the distant star. So light, in other words, is falling. It's falling to us from the distant star according to a geodesic line of space-time produced by the heavy gravitating body of the sun. And he made a prediction of 1.7 arcsecond for a sun, for a light beam coming from a distant star just grazing the surface of the sun, as to the deflection that would be impacted by the gravitation of the sun. Only many years later, Arthur Eddington, a British astronomer and physicist who claimed to be one of the only two people in the world to understand the theory of relativity, went out on a mission. There was a solar eclipse somewhere in a jungle kind of setting, and the expedition struggled to get pictures that would allow them to see a distant star when the eclipse was full, and then calculate the deflection of the starlight. And you can see here by these horizontal lines that in fact the light from the star is deflected, and it corresponded exactly to Einstein's predicted 1.7 arc seconds. So here was a prediction from the mathematics and the reconceptualization of space-time and gravity that was borne out by observation. So this is then what a toy solar system would look like. You have the sun here and the planets going around, not being pulled in by the sun, but following the path subject to the deformation and rearrangement of space-time itself. So the object just moves straight ahead. A body in motion will move forever, as one of Newton's laws of motion. But the path they take, they can only take the path to the space-time available to them. Now, Einstein published this theory around 1915. A copy of his, or preprint we would say today, of his paper arrived at the Russian front in World War I. A physicist, seen here in this image, doing calculations, was drafted to calculate the trajectory of artillery that was used in the battle. The paper that Einstein had written came to his attention, and being a brilliant physicist and mathematician, he noticed something that Einstein had not noticed. He was able to solve some of these elaborate differential equations of Einstein's theory and find a unique, exact solution. Even today, as we calculate space-time distortions, we use supercomputers to approximate numerical solution to these equations. This one is different. This is an exact solution to Einstein's equation, and it describes the so-called Schwarzschild radius. And it describes a phenomenon where gravity becomes so strong that space-time itself curves into itself, and that nothing can escape because of the severe distortion of space-time itself. Not even light, as you know, can escape a black hole. That's why it's called a black hole. Now, what Schwarzschild did is he put a number on the radius, the Schwarzschild radius, an imaginary line in space that looks like any other area in space, but once you cross it, your fate is sealed. You can never return, and you will progress slowly with increasing acceleration into the black hole, in the so-called singularity. The singularity being a place where the mathematics of relativity totally breaks down. We cannot make any statements because of infinite quantities adding up into extremely small volumes. Now, Einstein got a letter from Schwarzschild. The two men communicated, and Einstein could not find anything wrong with Carl's mathematics, and he said so. I cannot assail your mathematics, but you and I probably agree that this kind of thing can't happen. This object, this singularity, just can't exist. It just doesn't make sense. Einstein believed in order, in nature making sense and being accessible to our investigation and mathematics. So the belief that the theory would break down was just not acceptable to him, and he wrote this off as a mathematical quirk. Although the mathematics was unassailable, there was nothing wrong in the calculation, but he severely doubted the reality of it representing a real phenomenon in nature or a real object. So Einstein failed to accept his own prediction, which emanated from his very theory, pointed out to him by a fellow physicist whose mathematics he found unassailable. So the idea of black holes persisted in the imagination of astronomers and physicists. The story was strengthened significantly when astronomers discovered that at the center of galaxies, some weird things are going on. The image that you see here are the trajectories of stars imaged over the course of years and plotted, indicate that the speed by which these stars circle a dark object in the center of the galaxy is so fast that an incredibly massive object has to be there in order to make sense of these geodesics that Einstein's relativity predicted. But there's no star, there's no visible star, indicating perhaps Schwarzschild was right. Maybe there is a black hole, an infinitely dense, massive object that cannot be visualized because it does not emit any light. Now, these images were from UCLA, and the researchers there have plotted these geodesics, these paths of the stars over many, many years with extremely advanced technology. Technology had to really advance terrifically since Einstein's days in order for us to go ahead and test the implications of his theory. So again, the pathways that you see here and in the next brief video suggest that there is a massive, many, many times the mass of our sun residing in the center of our galaxy. Similar events have been seen in other parts of the universe, indicating that black holes might exist after all. So here is a image of the collaboration that we will discuss next, the so-called Event Horizon Telescope. This was started by Shep Doeleman and perhaps 20 or so collaborators. Since then, the group has grown to 200 plus on several continents. They have plugged away in finding a method to perhaps image what you should see if a black hole is really real. Namely, you should see a shadow from which light cannot be emitted, the Schwarzschild radius, the point of no return. And around that shadow should be a glowing mass of gas. It turns out that black holes must rotate, often at terrific speeds, sometimes approximating a good fraction of the speed of light. And this event, the black hole pulling in gas and spinning, heats the gas to incredibly high temperatures. So what you should see is a shadow surrounded by a ring of very, very hot gas, and that should be imageable. You should be able, with radio telescopes, to find this. The group was encouraged by a finding like this. Here in Virgo galaxy M87 is a phenomenon that produces a gigantic jet. As you can see, you can only see the jet coming at us slightly off center. You cannot see it going in the other direction because that we cannot visualize that. So there is a extremely powerful event happening, originating in a very small area of space, producing prodigious amounts of energy and matter being thrown for light years into the universe. What can power such an event? Theoretical physics tells us that the only imaginable source is a feeding frenzy of a black hole, which would heat the corona or the circulating gas it feeds upon to such extraordinary temperature, and the rotation would then have these jets produced in either direction. Here is another image that shows a jet like this in both directions now. This is an X-ray image at very, very high energies. So we know there are these phenomena that cry out for an explanation, and the likely explanation appears to be black holes. Okay, so to make a long story short, early in 2019, Shep Doeleman and his team, the Event Horizon Telescope, published this image. And this image corresponds exactly to the prediction made by Einstein's relativity for what a black hole should look like. Now, Einstein did not believe that these things existed, although his theory clearly predicted them. And using his theory, his mathematics, the researchers can predict from the supposed mass of the black hole, its speed of rotation, what the image might show. And as you can see in the center, you have the shadow surrounded by glowing gas. Now at the bottom, the gas appears to be hotter than at the top. That's because of a Doppler effect. The plane is not aligned properly, so you can see the approaching gas much faster and shifted towards higher energy spectrum than the gas in the back of the black hole. The Event Horizon team is extremely cautious, and as you will see in a moment here in a brief video, the kind of data they collect from multiple telescopes, radio telescopes in multiple sites and several continents, are stored on hard drives that are flown by jet to a central computer and analyzed there in an elaborate procedure to make sure that they don't trick themselves into seeing things that aren't there. Several teams of the Event Horizon community analyzed the data separately using individual algorithms and data sets. And lo and behold, as you can see in this slide here, the data sets agree and similar images are developed by Team 1 through Team 4, adding tremendous confidence that this is not some imaginary computer fluke or fluke in the data, but rather a real finding. This is an image of Shep Doeleman, who has been the driving force behind this and the inspiration. There are videos on YouTube you can see for him describing this adventure. I show you here in the next slide the first paper published in Astrophysical Journal entitled First M84 Event Horizon Telescope Result, The Shadow of the Supermassive Black Hole. This is an astonishing finding. From 1915 to 2019, 100 plus years of developing a theory, doubting it, finding pieces of suggestive evidence, to taking this giant leap of finding the darn thing and then nailing this down. So this is really the best of human collaboration and human science. It shows the power of prediction. It shows the power of taking predictions that come from solid theory seriously and attempting to track down the consequences with empirical evidence. This is the kind of best science that you can imagine. This is the inspiration, I think, that we need to take with us as we consider other predictions that might affect our life. In this next slide, you see the different telescopes that were involved. Hawaii, South America, Europe, up to the Arctic, and Antarctic, I should say, to the Chilean desert, a huge collaboration which will be expanded. The plan is to get finer and finer images of the black holes and eventually develop movies that show the black hole in action, feeding and behaving in its own distorted space-time environment. I will now show you a brief video in which the team describes how this was done and how the result was obtained.
What you're going to see here is this is what happens when you have only two stations. When you have Mexico and Arizona together, this is the virtual aperture, the virtual telescope I was showing you before. You want it with two little points here. All you can really tell is the size of the source. You get this blob. It's when you add a third station, here the Chilean station, the Atacama Desert, then since they're all kind of on a line here, all you can really tell is that it's a little bit smaller than it was before. It's when you add this outrigger in Hawaii, that's when you begin to see enough of a triangulation that this ring starts swimming into view. And after you get the European telescope, that's when you get that ring. So in the future, what we want to do is we want to add more telescopes to the array to sharpen our focus and to bring all these features more finely into detail than we have before. Now, what you're going to see here is an animation. I'm going to walk you through this a little bit. Here you'll see the Earth rotating. And every time you see two telescopes active, that bar will be flashing. And you'll see, in an additive way, all of the telescopes contributing to this virtual aperture, this virtual dish. And here you'll see the actual data, and I'll show you what that means in a moment. And these are the three different techniques that we used. So the first thing you see is the Earth is rotating. You're collecting some of the data. And you see all the different techniques getting better and better and better in completely different ways as you add more data. Okay, and by the very end, it's still rotating here. This is the plot I was telling you about before. So what you're seeing here is you're seeing the amount of energy that is detected on two of these dishes. For example, the one linked here by this purple line, versus the distance between those dishes. Right? So the farther away you get, the higher resolution your telescope is. When you're over here, your telescope does not have very high resolution. Here you're looking at large-scale structure. Here you're looking at very, very finely grained structure.
Now, we come now to a different set of predictions. We have talked in previous videos about the climate change that is surrounding us now and the grave predictions that have been made. And we discussed our reluctance to fully face up to the prediction of the models that have become increasingly accurate, provided by climate researchers. This is a huge community now. Einstein did his theory by himself with the help of Marcel Grossman and perhaps a couple of other people. Goleman had a team of 20 to 200. The climate community is thousands, 4,000 or more by now, of researchers dedicating their life to describing, analyzing, and tracking and predicting what is happening on our Earth in terms of climate. Now, I know what is happening. And how do I know? Well, I lived in California for 40 odd years. And in the last 2 or 3 years, something has changed. And what has changed is fire. Fire season used to be in the summer, perhaps early fall. Now it seems fire season is extended. The nature of fire has dramatically changed to high intensity fires that are so hot that they create their own local weather, creating fire tornadoes, events and phenomena previously unheard of. I'll show you a brief video of the fire season of 2019. My house is kind of in the middle of this, so this is affecting me directly. I get the smoke coming over when we have a major fire. There was a time when we had fires to the east and west of us, just a few miles from our home. So being in the middle of it gives you a very, very visceral perspective on the changes that have occurred in the last few years in the climate here in California. So I'll let you see the video and I'll see you back on the other side. So in this year, 2019, climate scientists have rung the alarm with increasing urgency and frequency. The International Panel for Climate Change, IPCC, is a multinational body of thousands of climate scientists that is very conservative and tries not to alarm people as to what we're up against if we continue to increase CO2 emissions. They now have woken up to a different set of circumstances. They have underestimated the interaction, the mutually enhancing interaction of various climate phenomena, which at the ultimate cause are driven by CO2 emissions, but then have trigger points that amplify the effects beyond recognition. One prediction is that global food production is headed for trouble. Western North America, regions in Western Russia, other regions will be impacted by climate change and will lead to noticeable difficulty in food production, and soaring prices are predicted as a result if this continues. Here is a plot of very recent origin where the level of risk of very dramatic escalating feedback changes is plotted against the year. Now you see here the last one is 2018, and we are here at 1 degree warming after pre-industrial levels, from pre-industrial levels. And you can see by the red color that we are approaching moderate to high levels of risk of escalating feedbacks, which will make the system tilt out of control, at which point no intervention in the world will prevent catastrophic changes. So here then are some of the interacting climate systems. We have the Amazon rainforest, which used to be a carbon sink. CO2 will be absorbed in a major way. Now we are burning large stretches of the Amazon rainforest, which may now become a carbon source. The Arctic sea ice is like a reflecting shield that prevents sunlight from warming the ocean, because it reflects sunlight right back into space. However, the extent of sea ice in the summer in the Arctic has been decreasing dramatically, leading to ever increasing rates of temperature increase. If this continues, it will have feedback effects on many other systems in the world. For example, the Atlantic circulation, what we call the Gulf Stream, going into Europe and keeping England and Northern Europe at moderate temperature, may collapse. Boreal forests are burning in Siberia. Permafrost adjacent to the Arctic is thawing in a major way, releasing carbon compounds which are much more thermogenic than, for example, CO2 itself. Methane is one of these gases, and methane has been increasingly detected in the permafrost regions, but also leaking from gas and oil installations all over the world. Turns out that methane is 80 or 90 times more potent as a heat-trapping gas compared to CO2. So here's another image in the next slide of the interacting factors. There's the cryosphere. We discussed the Arctic. Antarctic seems to be getting into trouble as well. And we have circulating patterns that are affected and so forth. In the next slide, here's a statement from the Potsdam Institute, which is one of the leading German research institutes dealing with climate change, stating that we have underestimated the risk of unleashing irreversible changes where the planet self-amplifies global warming. That is what we are seeing now, already at 1 Celsius global warming, where we are now. Scientifically, this provides strong evidence for declaring a planetary state of emergency. All right, so this is the data, these are the predictions, and we have trouble with predictions. We doubt them. We have some motivated reasoning. We have cynical actors like the oil and gas companies, which spent millions of dollars in creating smoke screens and false advertising that this ain't real. Very much akin to the tobacco industry stating that, we really don't have proof that smoking causes cancer. Well, yes, we do. But it took decades for this to be taken in seriously. And we don't have decades. It's been estimated we may have 7 to 10 years left to cut our carbon emissions to zero. That ain't gonna happen. We're not gonna do it. We have to do like 10% per year. In fact, what we're doing now is increase every year our carbon emissions. So our remaining carbon budget that we can safely burn to stay below 1.5 centigrade is running down very, very rapidly. Now there's an interesting sign of hope in a sense. Person of the Year in the next slide by Time magazine is Greta Thunberg, the 16-year-old teenager from Sweden who has become a spokesperson for climate activism and attempting to wake us up to the reality of climate change. She has become very powerful as a representative of our concerns and being a youth on top of it. Her generation will bear the consequences of our generation and the one before failure to address these problems, to realize the power of these predictions and take appropriate action. It's interesting, while impeachment hearings were going on for President Trump in the House of Representatives, he tweeted addressing Greta Thunberg, saying that she has an anger management problem and should deal with that and perhaps go see some movies with her friends. That's the response of the leader of our government to this spokesperson. I want to close this out by having Greta speak to you herself. And I hope that her emotionalism and her seriousness and her deep knowledge of the issues will make an impact on your own thinking. Thank you for your attention, and we'll see you soon again at Behavioral Health 2000.
This is all wrong. I shouldn't be up here. I should be back in school on the other side of the ocean. Yet you all come to us young people for hope. How dare you? You have stolen my dreams and my childhood with your empty words, and yet I'm one of the lucky ones. People are suffering, people are dying, entire ecosystems are collapsing. We are in the beginning of a mass extinction, and all you can talk about is money and fairy tales of eternal economic growth. How dare you? For more than 30 years, the science has been crystal clear. How dare you continue to look away and come here saying that you're doing enough when the politics and solutions needed are still nowhere in sight? You say you hear us and that you understand the urgency. But no matter how sad and angry I am, I do not want to believe that. Because if you really understood the situation and still kept on failing to act, then you would be evil, and that I refuse to believe.